Picture this. You're floating near the edge of a black hole, watching as seconds stretch into hours for everyone back on Earth. Your heartbeat slows, your thoughts crawl, and the universe itself seems to bend around you. This isn't science fiction, it's the real, mind-warping nature of time in our cosmos. Time isn't just a ticking clock, it's a cosmic trickster, bending, warping, and even vanishing under the right conditions. From black holes where time grinds to a halt, to particles that seem to remember the future, the universe plays by rules that defy everything we think we know. Buckle up, because we're about to unravel 30 of the most astonishing facts about time, facts that will twist your perception of reality and leave you questioning everything. By the end of this journey, you'll never look at a ticking clock the same way again. Ready to have your mind blown? Let's dive in. Now let's take our first step into the cosmic funhouse of time with a phenomenon so strange, it feels ripped straight from a sci-fi blockbuster. Picture this, you're orbiting a black hole, clinging to your ship as the universe's most extreme stopwatch kicks in. Time doesn't just slow down here, it practically drags its feet. Thanks to Einstein's theory of general relativity, we know gravity doesn't just pull on objects, it bends the very fabric of time itself. The stronger the gravity, the more time stretches like taffy. Near a black hole where gravity is so intense even light can't escape, time slows to a crawl compared to someone lounging on Earth. Think of it like that unforgettable scene in Interstellar, where the crew on the water planet near Gargantua ages minutes while decades pass for their colleague waiting in orbit. That wasn't just Hollywood magic, it was physics in action. Scientists call this effect gravitational time dilation, and we've actually measured it in real life. Atomic clocks placed at different altitudes, like on a mountaintop versus sea level, tick at slightly different rates because Earth's gravity isn't uniform. The difference is tiny, but near a black hole, it's extreme. A single hour for you could mean years, centuries, or even millennia for everyone else. Now, here's where it gets even wilder. This isn't just some abstract theory scribbled on a chalkboard. We've seen it play out in the cosmos. Take the star S2, orbiting the supermassive black hole at our galaxy's center. As it swings closer to the black hole's grip, its light shifts to redder wavelengths, a telltale sign of time slowing down in Einstein's playbook. Even GPS satellites orbiting Earth have to account for time dilation, adjusting their clocks to stay in sync with ground stations. If they didn't, your navigation apps would steer you into a ditch within minutes. So next time you check your watch, remember, time isn't the steady drumbeat we think it is. It's a cosmic rubber band, stretching and squeezing depending on where you stand in the universe's gravitational playground. And if you ever find yourself near a black hole, don't forget to send a postcard. Just be prepared for your family to receive it a few centuries late. Here's how you could transition into fact 2 while keeping the energy high and the explanation crystal clear. Now, imagine stepping out of that black hole's grip and racing across the cosmos at breakneck speeds, because time doesn't just bend under gravity's weight. It also warps when you're moving fast enough. This brings us to our next mind bender. The universe has no universal clock. Forget the idea of a single cosmic metronome ticking away for everyone. Time is more like a playlist where every listener gets their own tempo. Einstein's relativity tells us that time isn't absolute, it's personal. Picture this, twin siblings decide to test fate. One stays on Earth, sipping coffee and binge-watching shows, while the other boards a starship and zooms off at near light speed. When the traveling twin returns, they'd step off the ship looking barely older, while their Earth-bound sibling might have aged decades. This isn't sci-fi, it's the twin paradox, a real consequence of time dilation. The faster you move through space, the slower you move through time. Your starship isn't just breaking speed records, it's hitting pause on your personal clock. But here's where relativity gets downright useful. Those GPS satellites guiding your road trips, they're hurtling around Earth at nearly 9,000 miles per hour. At that speed, their onboard clocks tick just a tiny bit slower than clocks on the ground. But there's a twist: they're also farther from Earth's gravity, which makes their clocks tick faster than ours. These two effects don't cancel out, they battle for dominance, and gravity wins by a hair. Without engineers accounting for this, your GPS would be off by about 7 miles a day. That's the difference between reaching your destination and winding up in a lake. So why does this happen? Because space and time are woven together into a single fabric spacetime, and your motion or position literally tugs on the threads. A clock on a speeding train, a mountaintop, or a distant planet isn't wrong. It's just playing by the rules of its own local reality. Even your head ages a fraction of a second faster than your feet over a lifetime, thanks to Earth's gravity pulling harder on your lower half. The universe isn't just stranger than we imagine, it's stranger than we can imagine. And if time is this slippery in our own cosmic backyard, just wait until we venture deeper into the rabbit hole. Next up, we'll ask an even more unsettling question. What if time isn't real at all? But here's where things get even stranger. What if time itself is nothing more than a trick of the mind? Buckle up, because we're diving into fact 3. Time might be an illusion. That's right, the steady tick of the clock, the feeling of moments slipping past it, could all be a grand cosmic mirage. Some of the brightest minds in physics are questioning whether time is a fundamental feature of the universe or just a handy story our brains tell us to make sense of chaos. Take the block universe theory, for example. Imagine the entire history of the cosmos, past, present, and future, laid out like frames in a film. In this view, every moment exists simultaneously, frozen in place. Your birth, the dinosaurs, the heat death of the universe, they're all equally real, just stacked in an unchanging block of space-time. This isn't science fiction. It's a legitimate interpretation of Einstein's equations, where time is just another dimension, like length or width. The now you're experiencing, it's just your consciousness moving through the block, like a spotlight sweeping across a stage. Physicist Carlo Rovelli takes this even further. In his radical view, time isn't just flexible, it's downright optional. At the most fundamental level, he argues, the universe might not need time at all. Think about how we measure time. Clocks rely on regular, predictable motions, like the swing of a pendulum or the vibration of atoms. But zoom in close enough, and even those rhythms get fuzzy. Quantum particles don't follow neat, orderly beats. They pop in and out of existence in a blur of probabilities. Rovelli suggests that without these reliable rhythms, time as we know it dissolves. It's like trying to measure the speed of a river when the water itself keeps vanishing. So why do we feel time flowing? Blame it on entropy, the universe's tendency toward disorder. We remember the past but not the future because entropy increases in one direction, creating an arrow of time. A shattered glass reassembling itself would violate this law, which is why it feels so unnatural. But here's the kicker: entropy might just be a statistical quirk, not a cosmic rule. In an infinite multiverse, there could be pockets where entropy decreases and time runs backward. This isn't just philosophical noodling. If time is an illusion, it could reshape everything from quantum mechanics to artificial intelligence. An AI unshackled from human notions of time might process information in ways we can't fathom. Or consider quantum computers, which already exploit timeless probabilities to solve problems. The more we peel back the layers, the clearer it becomes. Time might be the universe's greatest magic trick, one we're only beginning to unravel. And if that's not mind-bending enough, wait until we explore what happened in the very first second of the universe's existence, when time as we know it blinked into being. Now, let's rewind the cosmic clock to the very beginning, when time itself flickered to life. Fact 4 takes us to the Big Bang's first second, a moment so unimaginably dense and hot that our usual rules of physics simply didn't apply. Picture this, the entire universe squeezed into a space smaller than a single atom, with temperatures soaring above 100,000 trillion degrees. In that first sliver of a second, the universe didn't just expand, it exploded into existence with a violence that defies comprehension. Here's the wild part: time as we know it didn't exist before this moment. There was no before the Big Bang, because time and space were born together in that initial fireball. Scientists call this the Planck epoch, a fleeting fragment of time just 10 to the power of minus 43 seconds, where gravity, the forces of nature, and even the concept of cause and effect were jumbled into a quantum fog. The laws of physics as we understand them today, they hadn't taken shape yet. It's like trying to use a weather forecast to describe the inside of a tornado. Then came cosmic inflation, the universe's most dramatic growth spurt. In less than a trillionth of a second, space itself stretched exponentially, smoothing out wrinkles and laying the groundwork for everything to come. This wasn't just fast, it was faster than the speed of light, a cosmic loophole allowed because empty space, not matter, was doing the expanding. Think of blowing up a balloon with galaxies painted on its surface. As the balloon inflates, every point races away from every other point, no center required. By the end of that first second, the universe had cooled just enough for protons and neutrons to snap together like Lego bricks, forming the first atomic nuclei. The energy was still so intense that particles collided, annihilated, and reborn in a frenzied dance. It's a scene we've recreated in particle colliders, but even our most powerful machines can't fully replicate those extreme conditions. What's truly humbling is how much of this remains a mystery. The Big Bang's first second is like the opening page of a book where the ink has faded. We can piece together fragments, but the full story eludes us. And yet, these fleeting moments set the stage for every galaxy, star, and ultimately us. Next up, we'll explore how this chaotic beginning might hold the key to time travel, because if time could bend at the birth of the universe, who's to say we can't bend it too? Now, here's where things get even wilder. We've talked about how the universe warps time, but what if you could actually ride those twists and turns into the future? Fact 5 dives into the astonishing reality that time travel to the future isn't just science fiction, it's a real, testable phenomenon, thanks to Einstein's theory of relativity. Let's break it down. If you could board a spaceship and accelerate to near the speed of light, time would slow down for you compared to everyone on Earth. Imagine you blast off on a 5-year mission at 99% light speed. When you return, you might have aged 5 years, but back on Earth, decades or even centuries could have passed. Your friends and family would be long gone, but you'd step out of your ship barely older than when you left. This isn't hypothetical, it's how relativity works. The faster you move through space, the slower you move through time, and you don't even need a light-speed engine to see this in action. Scientists have measured these tiny time shifts right here on Earth. In the 1970s, researchers placed atomic clocks on airplanes flying in opposite directions. When they compared them to clocks on the ground, the flying clocks were slightly behind, just nanoseconds, but enough to prove Einstein right. Even astronauts on the International Space Station, orbiting at 17,000 miles per hour, age a fraction of a second slower than we do. It's called time dilation, and it's your ticket to the future if you can go fast enough. But speed isn't the only way to time travel. Remember those black holes we talked about earlier? Orbiting one would have the same effect. Get too close to that gravitational monster, and time for you would crawl while it races forward elsewhere. In the movie Interstellar, Cooper's hours on Miller's planet near Gargantua cost him 23 years of Earth time. That's artistic license, but the physics checks out. The stronger the gravity, the more time bends. Now, before you start packing for the year 3000, there's a catch. The energy required to reach near light speeds is mind-boggling, far beyond our current technology. And surviving the G-forces or the spaghettifying pull of a black hole, That's another nightmare, but here's the kicker, the math doesn't lie. Time travel to the future is baked into the universe's rules. It's not a question of if but when we'll crack the engineering. So what's stopping us? For one, there's no coming back. This is a one-way trip, and the social implications. Showing up centuries later would make you a stranger in your own world. But for now, the fact that time travel is even possible should blow your mind. After all, if the universe allows it, who's to say we won't pull it off someday? Next up, we'll explore why time only seems to move forward, and how a shattered glass might hold the secret to the arrow of time itself. Moving from the mind-bending possibilities of time travel, let's tackle a far more familiar yet equally mysterious aspect of time: its stubborn insistence on moving forward. Fact 6 brings us face to face with the arrow of time, the one-way street that shapes our entire existence. Unlike the reversible equations of physics, which work just as well backward as forward, time has a clear direction, past to future. And the reason for this, it all comes down to a concept called entropy, the universe's obsession with disorder. Picture this: a glass slips from your hand and shatters on the floor. You've just witnessed the second law of thermodynamics in action. This law states that in any closed system, like our universe, entropy or disorder always increases over time. Those shards will never spontaneously reassemble into a pristine glass, no matter how long you wait. Why? Because high entropy states like broken glass are far more likely than low entropy ones like intact glass. There are countless ways for things to be disordered, but only a few precise arrangements for them to be ordered. This asymmetry is what gives time its arrow. We remember the past because it was more ordered. The future is forgotten because it's a messier, more probable state. But here's where it gets fascinating. The laws of physics themselves don't care about time's direction. If you watch a video of two billiard balls colliding and bouncing apart, you couldn't tell if the video was playing forward or backward. The physics works either way. Yet, if you saw a video of a shattered glass piecing itself together, you'd instantly know it's reversed. The difference: entropy leaves fingerprints. It's why we never see smoke flowing back into a cigarette or cream unstirring from coffee. These processes are irreversible because they increase the universe's disorder. Now zoom out to the cosmic scale. The Big Bang kicked off the universe in an incredibly low entropy state, a hot, dense, and highly ordered soup of particles. Since then, the universe has been relentlessly climbing toward higher entropy, like a winding clock you can't rewind. Stars burn out, black holes evaporate, and energy spreads thin. Even your morning toast follows the rule. The heat from the toaster disperses into the air, never returning to the bread. This relentless march toward disorder is why we perceive time as flowing forward. So what does this mean for us? It explains why you can't unscramble an egg or undo your childhood. It's why nostalgia hits harder than déjà vu. The past is a fixed, orderly memory, while the future is an open sea of possibilities. And it hints at a profound truth. Time's arrow isn't just a feature of the universe. It's the reason we experience cause and effect, aging, and even the very concept of change. Without entropy, time would lose its meaning and reality would be a static, directionless blur. Next up, we'll explore an even stranger twist: how time itself grinds to a halt at the speed of light. Strap in, this one bends the rules even further. Now, let's push the boundaries of time even further. What if I told you that time itself could come to a complete standstill? Fact 7 takes us straight to the heart of Einstein's theory of relativity, where the speed of light isn't just a cosmic speed limit, it's a place where time ceases to exist. Imagine you're a photon, a tiny particle of light racing through the vacuum of space at roughly 300,000 kilometers per second. From your perspective, something extraordinary happens. Time stops. Not slows down, not distorts, it freezes entirely. Here's why. According to Einstein, as an object approaches the speed of light, time dilation becomes so extreme that for the moving object, time effectively grinds to a halt. For a photon, the journey from a distant star to your eye isn't a trip that takes years or millennia, it's instantaneous. No matter if the photon traveled across the room or from the edge of the observable universe, from its point of view, there's no passage of time at all. This isn't just a wild thought experiment, it's baked into the math of relativity. The faster you go, the more time slows down for you relative to someone standing still. At light speed, the equations break in a fascinating way. Time's denominator becomes zero, meaning time itself loses all meaning. This is why photons don't experience time. They're born in a star's fusion reaction and arrive at your retina. From their perspective, both events happen simultaneously. The implications of this are staggering. First, it reshapes how we think about distance in the universe. That twinkle of a star 1,000 light-years away. From the photon's viewpoint, it didn't spend a millennium traveling. It arrived the instant it was emitted. Second, it highlights just how relative time really is. Your experience of time depends entirely on your speed and gravitational environment. A cosmic ray particle zipping through space at near light speed might decay in microseconds from our perspective, but for the particle, its entire lifespan could feel infinitely shorter. But here's the real kicker: this effect isn't limited to light. If you could somehow ride a beam of light, the entire universe would appear frozen around you. Distant galaxies, aging stars, even the pulsating core of a black hole, all would seem like a snapshot, unmoving. It's a reminder that time isn't some universal backdrop. It's a flexible, personal experience shaped by motion. So next time you bask in sunlight, remember those photons didn't just cross 93 million miles of space. From their perspective, they left the sun's surface and landed on your skin in the same instant. And that's the mind-bending truth. At light speed, the universe doesn't just bend time. It erases it entirely. Up next, we'll tackle another cosmic puzzle: why the universe's age and its observable size don't quite match up. Get ready for a journey to the edge of what we can see. Here's a seamless continuation of the script, diving into the fascinating disconnect between the universe's age and its observable size. Now, let's unravel one of cosmology's greatest head-scratchers: how the universe can be younger than the space it fills. At first glance, it sounds impossible. If the universe is 13.8 billion years old, how can we see galaxies over 93 billion light-years away? Shouldn't the observable universe be, at most, 13.8 billion light-years in radius? The answer lies in the universe's most relentless force: expansion. Picture the cosmos as a balloon inflating. If you dot the balloon with tiny marks representing galaxies as it expands, those marks grow farther apart. Now imagine light traveling from one mark to another, but while it's in transit, the balloon stretches, stretching the distance the light must cover. This is exactly what happens in our universe. When light from the most distant galaxies began its journey billions of years ago, space itself was far more compact. But as the light traveled, the universe expanded, carrying galaxies away from each other. By the time that light reaches us, the source galaxy has moved much farther than its original distance. That's why the observable universe stretches 93 billion light-years across, even though the light from its edge only traveled for 13.8 billion years. But here's where it gets even stranger. The farthest light we can see, the cosmic microwave background radiation, is like a postcard from the universe's infancy, sent when it was just 380,000 years old. Beyond that, there's a cosmic horizon, not because space ends, but because light from anything farther hasn't had enough time to reach us yet. It's like standing on a shore, gazing at a foggy ocean. The horizon isn't the edge of the water, it's just the limit of how far you can see. This raises a tantalizing mystery. What lies beyond our cosmic horizon? Is it more of the same: endless galaxies, stars, and planets? Or could there be regions where physics operates differently? Some theories suggest other bubble universes with their own big bangs, forever cut off from our observable reality. Others propose that space might be infinite, making our 93 billion light-year view just a speck in an unfathomable vastness. For now, this horizon remains one of science's great frontiers. Every new telescope peels back another layer, but the ultimate boundaries of reality might stay forever out of reach. And that's the humbling truth. We're not just studying the universe's past when we look deep into space. We're also confronting the limits of what we can ever know. Up next, we'll explore an idea that challenges everything about how time works. What if it's not continuous, but made of tiny, indivisible fragments? Get ready to shrink down to the smallest scales imaginable. Now, let's dive into one of the most radical ideas in physics. What if time isn't a smooth, flowing river, but more like a flipbook made of tiny, indivisible frames? This isn't science fiction. Some of the brightest minds in quantum physics are seriously exploring the possibility that time could be quantized, meaning it's broken into the smallest possible chunks, just like matter is made of atoms. The smallest unit of time we've theorized is called Planck time, a mind-bogglingly short interval of about 10 to the power of negative 43 seconds. To put that in perspective, if you could divide a single second into as many slices as there are atoms in the universe, you still wouldn't come close to the tininess of Planck time. At this scale, the very fabric of reality behaves so wildly that our current laws of physics simply break down. Why does this matter? Because it could be the key to solving one of science's biggest puzzles, unifying general relativity, which governs the cosmos on massive scales, with quantum mechanics, which rules the subatomic world. Right now, these two theories are like two brilliant but stubborn people speaking different languages. They don't agree on how gravity works at the quantum level. But if time is quantized, it might offer a common ground, a new framework where both theories can finally shake hands. Imagine watching a movie where the film strip is made of individual frames. Even though the motion looks smooth, it's actually a series of still images. If time works the same way, what we perceive as a continuous flow might really be a rapid succession of these Planck-sized moments. This could reshape everything from how we understand black holes to the very nature of causality. For instance, if time jumps between these frames, does that mean there's a smallest possible step for cause and effect? Could events unfold in tiny, discrete leaps instead of a seamless chain? Some theories, like loop quantum gravity, take this idea even further. They suggest that not just time, but space itself might be pixelated, woven from minuscule loops or grains. If true, this would mean the universe is more like a digital simulation than a smooth, analog reality, except there's no computer running it, just the fundamental rules of quantum mechanics. Of course, this is all still theoretical. We don't yet have the technology to probe time at the Planck scale, and some physicists argue that time might remain continuous no matter how deep we look. But the implications are too tantalizing to ignore. If time is quantized, it could rewrite our understanding of everything from the birth of the universe to the inner workings of black holes, where even time itself seems to stand still. Up next, we'll confront an even more haunting question. What if time itself has an expiration date? The universe might not just fade into darkness, it could face a far more dramatic end. Now, let's shift our gaze to the far future, where time itself might not just warp or slow down, but cease to exist entirely. One of the most chilling possibilities is the Big Freeze, a scenario where the universe keeps expanding forever, but all its energy gets spread so thin that stars burn out, black holes evaporate, and even atoms themselves decay. Imagine a cosmic graveyard where every particle is drifting infinitely apart, unable to interact, and entropy, the measure of disorder, reaches its maximum. Time wouldn't stop in the traditional sense, but with no change, no events, and no energy left to fuel processes, time would become meaningless. It's like a clock that's still ticking, but with no hands left to move. But that's not the only fate on the table. Picture the Big Rip, a far more violent end. Here, dark energy, the mysterious force accelerating the universe's expansion, grows so powerful that it overcomes gravity, electromagnetism, even the nuclear forces holding atoms together. Galaxies would be torn apart first, then stars, planets, and eventually, space-time itself would shred into fragments. In this scenario, time doesn't just fade, it's annihilated, as the very fabric of reality disintegrates. Now contrast these grim finales with the cyclic universe model, which offers a poetic alternative. Instead of an ending, time could reset in an endless loop. Imagine the universe collapsing back into a singularity, only to rebound in a new Big Bang like a cosmic heartbeat. In this view, our universe might just be one in an infinite series, each with its own laws of physics and arrow of time. Some theories even suggest that traces of past universes could linger, like echoes in the cosmic background radiation. So which is it? A silent, frozen eternity, a violent rupture, or an endless cycle of rebirth? The truth is, we don't know yet, but each possibility forces us to rethink what time really is. Is it a canvas for change, or just an illusion that vanishes when change runs out? Whether time ends with a whimper, a bang, or a reboot, one thing's certain: the universe has a way of keeping us humble. And speaking of humility, our next fact might make you question whether time even had a beginning at all. What if our universe is just one chapter in an infinitely old story? Here's the next part of the script, seamlessly continuing from the previous section while introducing fact 11 with a fresh and engaging transition. But before we dive into the mysteries of time before the Big Bang, let's bring things a little closer to home, literally. Believe it or not, time doesn't even tick at the same rate on Earth depending on where you are. That's right, if you've ever stood on a mountaintop, you've technically aged ever so slightly faster than someone at sea level. Sounds like science fiction, but it's pure Einstein. This bizarre effect called time dilation happens because gravity warps time. The stronger the gravitational pull, the slower time moves. So at sea level, where Earth's gravity is slightly stronger, clocks tick a tiny bit slower compared to those on mountaintops where gravity is weaker. We're talking nanoseconds here, but modern atomic clocks are precise enough to measure it. In fact, scientists have proven this by placing identical atomic clocks at different elevations and watching them drift out of sync. Here's a fun way to think about it. Your head actually ages faster than your feet. Since your head is farther from Earth's center, it experiences very slightly weaker gravity. Over a lifetime, the difference is negligible. We're talking fractions of a second, but it's a mind-blowing reminder that even the ground beneath our feet isn't a fixed stage for time. This isn't just a quirky thought experiment. GPS satellites have to account for time dilation to stay accurate. Orbiting high above Earth, their clocks run faster than those on the ground. Without constant adjustments, your phone's navigation would be off by miles within minutes. So, next time you use Google Maps, thank Einstein for keeping you on track. And remember, time is anything but universal, even in your own backyard. Now, if time can bend just by climbing a mountain, imagine how wild things get when we rewind to the very beginning. But let's shift our gaze from the heights of Earth to the depths of space, where another time-bending puzzle lurks, one that left scientists scratching their heads for decades. Enter the Pioneer anomaly, a cosmic glitch that challenged everything we thought we knew about motion and gravity. Back in the 1980s and 90s, as NASA Pioneer 10 and 11 spacecraft ventured beyond our solar system, something strange happened. Their trajectories didn't quite match predictions. Instead of coasting along as expected, both probes slowed down just a tiny bit more than physics said they should, as if an invisible hand was gently tugging them backward. At first, scientists brushed it off as a minor error, but when the discrepancy persisted year after year, it became impossible to ignore. What made this so baffling was the precision of spaceflight math. We can calculate a spacecraft's path down to the millimeter, accounting for every gravitational nudge from planets and even the pressure of sunlight. Yet here was Pioneer defying the rules without any obvious explanation. Some wondered if it was a sign of new physics, a flaw in Einstein's relativity, or a hint of unseen dark matter tugging at the probes. Others proposed wilder ideas like modified gravity laws or even unseen dimensions warping spacetime itself. Then came the aha moment. After years of head-scratching, researchers realized the culprit wasn't exotic physics at all, it was something far more mundane: heat. The spacecraft's radioactive power sources, called RTGs, were emitting warmth unevenly. That tiny thermal radiation acted like a mini thruster, pushing Pioneer backward ever so slightly. Case closed, not entirely. While heat explained most of the anomaly, some lingering questions remain. Could there still be undiscovered forces at play in the cosmos? The Pioneer anomaly taught us two vital lessons. First, even the tiniest overlooked detail, like a spacecraft's warmth, can upend our understanding of time and motion. Second, the universe loves throwing curveballs, nudging us to question what we think we know, and that's what makes exploring time's mysteries so thrilling. Every anomaly, every glitch is a doorway to deeper truths. Now, speaking of cosmic oddities, let's turn our attention to something even stranger, a form of matter that doesn't just exist in space, but in time itself. Just when you thought the universe couldn't get any weirder, along comes a discovery that flips the script on reality itself. Imagine a material that doesn't just sit there. It moves, oscillates, repeats, not because it's being pushed or pulled, but because that's simply its natural state. Welcome to the mind-bending world of time crystals. Unlike ordinary crystals, think diamonds or salt, whose atoms are arranged in repeating patterns in space. Time crystals have atoms that dance in repeating patterns in time. Picture a clock that ticks forever without any batteries, or a pendulum that swings on its own, never slowing down. That's the essence of a time crystal, a structure that cycles through states indefinitely without any energy input, defying one of the most sacred laws of physics, the second law of thermodynamics, which says systems should trend toward disorder, not perpetual motion. The idea of time crystals was first proposed in 2012 by Nobel Prize-winning physicist Frank Wilczek, and at first many scientists dismissed it as impossible. How could something keep rhythm without losing energy? But by 2017, two separate teams, one at Harvard, another at the University of Maryland, actually created time crystals in the lab using chains of ions or dense clouds of atoms chilled to near absolute zero. These systems, when nudged just right, began flipping between states like a cosmic metronome, ticking away in a loop that seemed to ignore the usual rules of entropy. Here's what makes time crystals so revolutionary. They exist in what's called a non-equilibrium phase of matter. Everything we know, solids, liquids, gases, relies on equilibrium, a stable state where energy is balanced. Time crystals break that mold. They're stable yet dynamic, like a frozen whirlpool that never stops spinning. And while they don't violate thermodynamics, they don't create energy, they do expose loopholes in our understanding of how matter behaves. The implications are staggering. Time crystals could revolutionize quantum computing by providing ultra-stable qubits, the building blocks of quantum processors that resist the decoherence plaguing current systems. Imagine a quantum computer that doesn't lose information because its components are locked in perfect, self-sustaining rhythms. Beyond that, time crystals might unlock new forms of precision sensors or even clues about the fabric of spacetime itself. Some theorists speculate they could model exotic phenomena like black holes or the early universe. But here's the kicker: we've only just scratched the surface. Time crystals exist in highly controlled lab conditions today, but what if nature has been hiding them all along? Could they lurk in the quantum froth of empty space or the heart of neutron stars? The hunt is on to find out, so while time crystals might sound like science fiction, they're very real, and they're rewriting the rules of reality one tick at a time. And speaking of rewriting rules, our next fact takes us back to the dawn of everything, where time itself might have played by a completely different set of them. Now, let's stretch our understanding even further, because the universe itself is doing just that. The Hubble expansion isn't just about galaxies drifting apart, it's a cosmic dance that warps time itself. Picture this: the farther away a galaxy is, the faster it seems to be rushing away from us. It's not that these galaxies are speeding through space, it's that the fabric of spacetime between us is stretching like dots on an inflating balloon. And this stretching isn't just about distance, it's intricately tied to how we perceive time on a grand scale. Here's where it gets mind-bending. As spacetime expands, the light from distant galaxies gets stretched too, shifting toward longer, redder wavelengths, a phenomenon called redshift. But this isn't just a visual effect, it's a time effect. That light has been traveling for billions of years, and its redshift tells a story about how the universe has aged. The deeper we look into space, the further back we see in time, like flipping through pages of a cosmic history book where the words themselves fade and stretch. What's even wilder is that this expansion isn't just happening out there, it's happening right here in the space between atoms. Right now, the force of expansion is too weak to overcome the bonds holding matter together. But what if that changes? Enter the Big Rip, one of the most dramatic possible endings for the universe. If dark energy, the mysterious force driving accelerated expansion, grows stronger over time, it could eventually overpower gravity, electromagnetism, even the nuclear forces holding atoms together. Picture a universe where, in the distant future, galaxies are shredded first, then stars, then planets, and finally, in a last violent instant, every atom is torn apart. Time as we know it would lose all meaning in a cosmos where nothing can hold itself together. But don't panic just yet. The Big Rip is still speculative, and many scientists argue that dark energy might stay constant or even weaken. What's undeniable, though, is that the Hubble expansion is reshaping our understanding of time's arrow. In a contracting universe, time might feel different, more cyclical, perhaps. But in our expanding cosmos, time has a direction, and everything from the fading light of ancient galaxies to the potential fate of matter itself is swept along in the current. So the next time you hear about the universe expanding, remember, it's not just space growing, it's time itself stretching and twisting in ways we're only beginning to grasp. And speaking of twists, our next fact takes us to the very edge of reality, where time might not even exist at all. Now, let's rewind the cosmic clock back before the Big Bang itself. What was time like when our universe hadn't even begun? This is where physics ventures into the realm of speculation, but the theories are as thrilling as they are mysterious. One leading idea is the Big Bounce, a cosmic reboot where our universe emerged from the collapse of a previous one. Imagine a pendulum swinging endlessly: contraction, bounce, expansion, repeat. In this model, time isn't a straight line with a single beginning. It's a loop, with each cycle birthing a fresh universe from the ashes of the old. But the Big Bounce isn't the only contender. Enter multiverse theory, where our universe is just one bubble in an infinite foam of others, each with its own laws of physics and arrow of time. Picture a cosmic kaleidoscope, where new universes constantly bud off from quantum fluctuations in a vast, eternal background. Some theories suggest these baby universes pop into existence inside black holes, their intense gravitational warps acting as cosmic wombs. If true, time might not have a single origin point at all. It could be a sprawling, branching tree with roots stretching back indefinitely. Then there's cyclic cosmology, which takes the idea of eternal return to a grand scale. In this view, universes collide and reset in an endless dance, like sheets of spacetime clashing together in higher dimensions. Each collision triggers a new Big Bang, erasing the past but preserving faint echoes in the cosmic microwave background, like shadows of a universe that came before. Here's the catch: all these theories grapple with the same enigma. At the moment of the Big Bang, our laws of physics break down. Gravity becomes quantum, particles lose meaning, and time, as we know it, ceases to function. Was there a before, or does the question itself make no sense, like asking what's north of the North Pole? Even cutting-edge ideas like loop quantum gravity or string theory struggle to paint a clear picture. Some physicists, like Stephen Hawking, argued that time itself began with the Big Bang, rendering before meaningless. Others, like Roger Penrose, hint at cryptic clues in the cosmic microwave background, anomalies that might be scars from a prior cosmos. So where does that leave us? With awe and a humbling admission, the origin of time remains one of science's deepest puzzles, but that's the beauty of cosmology. Every unanswered question is an invitation to imagine, to test, to push the boundaries of what we think is possible. And as we'll see next, even the strangest ideas, like universes budding from black holes, might hold a kernel of truth. Now, shifting our gaze from the birth of time itself to the mysteries hidden in the stars, let's talk about one of the most tantalizing cosmic enigmas, the WOW signal. Back in 1977, a radio telescope in Ohio picked up a blast of radio waves so powerful and unusual that an astronomer scribbled, "Wow," in the margins of the data printout. This 72-second burst came from the direction of the constellation Sagittarius, and to this day, it remains the strongest candidate for an extraterrestrial signal ever detected. But here's the twist: it never repeated, just a fleeting blip, gone as suddenly as it appeared. And that raises a mind-bending question: how do you communicate across the vast stretches of cosmic time? Think about it. If that signal was sent by intelligent beings, it likely traveled for hundreds of years before reaching us. By the time we heard it, the civilization that sent it might have vanished, evolved beyond recognition, or simply moved on. That's the tyranny of interstellar distances. Light and radio waves only move so fast. A simple hello between stars could span generations. Imagine sending a message to someone 1,000 light years away. You'd need to wait 2,000 years just to get a reply. It's like shouting into a canyon and hearing the echo return long after you've left. And then there's the WOW signal's bizarre duration, 72 seconds. Why that exact length? Some speculate it could be a beacon, deliberately designed to stand out against natural cosmic noise. Others wonder if it was a fragment of a longer transmission, a cosmic postcard we only caught a snippet of. But here's the eerie part: if it was artificial, the energy required to send it would dwarf anything humanity has ever produced. We're talking about a civilization harnessing the power of stars just to say, "We're here." This also highlights the challenges of active searches for alien signals. Projects like SETI, the search for extraterrestrial intelligence, scan the skies, but they're limited by time and technology. The universe is old, 13.8 billion years old, and intelligent life might have flickered in and out of existence countless times. We could be listening to a cosmic graveyard, picking up whispers from civilizations long gone. Or worse, our own signals might reach someone else long after we're extinct. So what's the takeaway? Time doesn't just warp near black holes or stretch at light speed. It also dictates whether we'll ever make contact. The WOW signal is a reminder that even if the universe is teeming with life, we might all be prisoners of time, shouting across the void with no guarantee anyone's listening. And as we'll see next, when we ponder the fate of civilizations across eons, time becomes more than a dimension. It becomes the ultimate cosmic filter. Now let's peel back another layer of time's mystery by looking at what happens in the emptiness of space itself. You might think a vacuum is just nothing. But here's the twist: even in the deepest voids of the universe, particles are constantly flickering in and out of existence like cosmic static. These are quantum fluctuations, tiny bursts of energy that defy our everyday intuition. And believe it or not, they might hold the key to understanding how time itself emerges. Picture this: in a region of space that seems utterly empty, pairs of particles and antiparticles spontaneously appear, exist for a fleeting moment, and then annihilate each other. This isn't science fiction, it's a fundamental part of quantum field theory, backed by mountains of evidence. These fluctuations happen on scales so small, they're measured in units called Planck time, about 10 to the power of minus 43 seconds. That's so brief, it makes a blink feel like an eternity. But here's where it gets even wilder. Some physicists, like Nobel laureate Richard Feynman, suggest that these chaotic, microscopic interactions could be the building blocks of time. Think of it like a flipbook. Each tiny quantum event is a single frame, and when you stack them together, you get the illusion of continuous flow, the time we experience. Feynman's diagrams, those squiggly lines physicists use to map particle collisions, hint at this. They show how particles interact in ways that aren't just linear but tangled, looping, even moving backward in time on those infinitesimal scales. So, what does this mean for our understanding of time? Well, if time emerges from these quantum jitters, it might not be the smooth, universal river we imagine. Instead, it could be more like a frothing, bubbling foam at the smallest levels, only appearing steady when we zoom out. This idea shakes the very foundation of how we think about cause and effect. Could now just be a statistical illusion, an average of countless quantum moments. And here's the kicker: if time is born from quantum chaos, it might not even exist at the most fundamental level. Theories like loop quantum gravity suggest that spacetime itself is granular, made of discrete chunks. No smooth continuum, just tiny, interconnected nodes where these fluctuations play out. That's why some physicists argue that time, as we know it, is a side effect of deeper physics, not a primary feature of the universe. So next time you glance at a clock, remember, those ticking seconds might just be the echoes of a quantum storm, a symphony of particles dancing in the void. And as we'll see soon, when we explore how consciousness stitches these moments together, the line between time and perception gets even blurrier. Here's your next section, flowing naturally from the previous content while introducing fresh insights on the Fermi paradox and time. Now, let's step back and consider a puzzle that haunts scientists and dreamers alike. Why, in a universe so vast and ancient, have we never heard from other civilizations? This is the Fermi paradox, and when you factor in the mind-boggling scale of cosmic time, it becomes even more unsettling. Imagine this: the universe is roughly 13.8 billion years old, and Earth is just 4.5 billion years young. That means countless stars and potentially life-bearing planets could have risen and fallen long before our solar system even existed. Here's the chilling thought: advanced civilizations might not just be elsewhere in space, they could be elsewhere in time. Think of it like missing a train by seconds. If another species reached its technological peak 1 million years ago, or won't emerge for another million, we'd never know. The cosmic calendar is so immense that even thriving empires could blink in and out of existence without overlapping. And that raises a haunting question: is humanity impossibly early or tragically late to the party? This ties into the Great Filter theory, a potential bottleneck that prevents life from advancing to interstellar scales. Maybe the filter is behind us, like the improbable leap from single-celled organisms to complex life. But if it's ahead of us, say, self-destruction through war or climate collapse, that's far grimmer. The silence of the universe might be a warning. Time swallows civilizations before they can ever meet. Yet there's another twist. Some researchers argue that ultra-advanced beings might transcend physical forms, becoming digital or post-biological. They could exist outside our perception of time, hiding in black hole computations or folded dimensions. If that's true, the Fermi paradox isn't about absence, it's about scale. We're like ants searching for other ants, unaware of the giants walking overhead. So where does that leave us? The paradox forces us to confront our fragility in time. Every second we delay becoming a multiplanetary species, we gamble with extinction. But it also sparks hope. If we survive the filter, humanity could one day be the ancient, advanced civilization others search for in the cosmic dark. And as we'll see next, even our consciousness might play tricks with time, bending reality in ways we're only starting to grasp. Now, let's turn inward, because time isn't just out there in the cosmos. It's inside us, shaping how we think, remember, and even feel. Here's the wild question: is time a real force of nature, or just a trick our brains play on us? Neuroscience reveals that our perception of time is shockingly flexible. Ever noticed how a boring hour drags while a thrilling minute flies by? That's your brain compressing or stretching time based on attention and emotion. Studies show that during high adrenaline moments like a car crash, your brain crams extra details into memory, making events seem to unfold in slow motion. It's not that time actually slows down. Your mind just records more frames, like a camera switching to ultra-high speed. But it gets stranger. Patients with certain brain injuries lose the ability to gauge time altogether. Imagine pouring tea and watching it freeze mid-air, never knowing when it'll hit the cup. This suggests time isn't just out there, it's a construct our brains assemble from sensory input. Philosophers like Kant argued this centuries ago. Time might be the lens through which we experience reality, not reality itself. Now contrast that with artificial intelligence. An AI doesn't have a biological clock or emotions to distort its sense of time. It could process a millennium of data in seconds or pause indefinitely between computations. For a superintelligent AI, time might feel more like a database to query than a river to swim in. This raises eerie possibilities. Could future AIs edit their perception of time, speeding up their subjective experience to solve problems faster? Or might they abandon time entirely, existing in a state of eternal now? Here's the twist: if time is just a human illusion, what does that mean for the universe? Some physicists propose that at the quantum level, time might not flow at all. Particles don't age or remember, they just interact. In this view, the past, present, and future could be equally real, stacked like pages in a book. Our conscious minds might just be reading one page at a time, mistaking the sequence for reality. So where does that leave us? Whether time is a physical law or a mental mirage, it's the glue of our existence. Lose it and memory, planning, even identity would crumble. Yet the universe hums along just fine without clocks, suggesting time, like color or sound, might be our brain's way of translating the cosmos into something we can understand. And as we'll see next, even the fabric of spacetime itself might have cracks where time simply stops. But before we unravel the mysteries of timeless singularities, let's rewind further, all the way to the very first tick of the cosmic clock. Picture this: the universe is so young, it hasn't even celebrated its first 10 millionth of a trillionth of a trillionth of a trillionth of a second. This is the Planck epoch, a fleeting moment when gravity wasn't the gentle force we know today, but a wild quantum beast. At this scale, the universe was a seething chaos where space and time didn't behave like the smooth fabric we're familiar with. Instead, they froth and churn like an ocean in a storm. The temperatures, a blistering 10 to the power of 32 degrees. The density, imagine cramming the entire mass of the universe into a space smaller than a single atom. Under these conditions, the very laws of physics as we know them, Einstein's relativity, Newton's gravity, simply dissolve. This is the ultimate frontier of cosmic mystery, a realm where time itself loses all meaning. Scientists call it the time before time, because our conventional ideas of past, present, and future cease to apply. String theory offers one tantalizing glimpse into this primordial madness. It suggests that the fundamental building blocks of reality aren't particles but tiny, vibrating strings. In the Planck epoch, these strings would have thrummed with unimaginable energy, twisting spacetime into knots. Some models even propose that extra dimensions beyond the four we experience unfurled and collapsed in a dizzying dance. But here's the catch, we can't yet test these ideas. The energies required to probe this era are a quadrillion times beyond what our most powerful particle colliders can achieve. So why does this matter? Because the Planck epoch holds the keys to the universe's deepest secrets. The quantum fluctuations that emerged here might have planted the seeds for galaxies, stars, and ultimately us. If we could decode this era, we might finally understand why our universe has the precise mix of forces and constants that allow life to exist. For now, though, it remains a shadowy chapter in cosmic history, a reminder that time, as we know it, is just a fleeting footnote in a far grander story. And as we'll soon see, even the idea of a beginning might be an illusion. Now, let's fast forward from the universe's fiery beginnings to its shadowy future, where an invisible force is quietly rewriting the rules of time itself. Dark energy, the mysterious culprit behind the universe's accelerating expansion, isn't just stretching space, it's stretching our understanding of time's destiny. Picture this, every second, galaxies farther away from us are being swept into the cosmic void faster, not because they're moving through space, but because space itself is growing between us. And this isn't just a slow creep, it's a runaway train. If this continues, the universe could end in a big freeze, where galaxies vanish over the horizon of visibility, leaving our night sky utterly black. But here's where things get eerie. If dark energy's grip strengthens over time, it could tear apart more than just galaxies. In a scenario called the Big Rip, dark energy might eventually overpower gravity itself, shredding stars, planets, and even atoms into nothingness. Time in this apocalyptic finale would lose all meaning. No clocks, no observers, just an endless, silent void. On the flip side, what if dark energy weakens or reverses? Some theories suggest it could decay into something else, causing the universe's expansion to slow or even collapse in a big crunch. Time might then fold back on itself like a tape rewinding, though physicists debate whether such a reversal would truly reset the cosmic clock or just create a chaotic new beginning. The strangest part, we have no idea what dark energy is. It makes up about 68% of the universe's energy budget, yet it leaves no fingerprints, no particles, no light, just a ghostly push against gravity. Some think it's woven into the fabric of space itself, Einstein's cosmological constant, while others propose exotic fields or even flaws in our theories of gravity. The truth is, every explanation feels like grasping at shadows. But dark energy's mystery isn't just academic, it's personal. The fate of time is, in a way, the fate of every story, memory, and civilization. If the universe keeps accelerating, future astronomers might gaze up at an empty sky with no clues that galaxies ever existed. It's a humbling reminder. Time isn't just a backdrop to the cosmos, it's a force as malleable and enigmatic as dark energy itself. And as we'll see next, even the flow of time isn't immune to the quirks of human experience, as astronaut Scott Kelly's twin paradox proved in real life. From the cosmic mysteries of dark energy, let's bring things a little closer to home, or rather, closer to orbit with a real-life experiment that proves time isn't just a theoretical playground. Meet astronaut Scott Kelly and his identical twin brother, Mark. Scott spent nearly 1 year aboard the International Space Station, hurtling around Earth at roughly 17,500 miles per hour, while Mark stayed firmly planted on the ground. When Scott returned, scientists made an incredible discovery. He had aged slightly less than his twin. Now, before you imagine futuristic anti-aging space vacations, the difference was tiny, about 8.6 milliseconds over 340 days. But here's why it matters. This minuscule gap is direct proof of Einstein's time dilation at work. The faster you move, the slower time ticks for you relative to someone moving slower. Scott's high-speed orbit meant his clock ran a hair slower than Mark's. Gravity played a role too. The weaker pull of Earth's gravity at the station's altitude sped up time slightly, counteracting the speed effect by about 4.5 milliseconds. Add it all up and Scott came home 8.6 milliseconds younger. But let's zoom out. This experiment wasn't just about bragging rights for the Kelly family. It's a sneak peek into humanity's interstellar future. Imagine a crewed mission to Mars where astronauts might spend 2 to 3 years in space. The time dilation would still be small but cumulative. Over decades of deep space travel, astronauts could return to an Earth that's aged years more than they have. Picture a scenario where a crew spends 20 years near light speed. They might come home to find their grandchildren older than they are, the real challenge. Biology, time dilation might spare astronauts milliseconds on the clock, but space itself isn't so forgiving. Prolonged exposure to microgravity weakens muscles and bones, cosmic radiation damages cells, and isolation strains mental health. Scott's mission revealed that even after returning, some of his genetic expressions and immune responses hadn't fully bounced back. Time might bend, but our bodies still obey Earth's rules for now. So what's next? With plans for lunar bases and Mars colonies, scientists are racing to understand long-term space effects. Could artificial gravity or new medicines offset these hurdles? And if we ever crack near light-speed travel, will humanity split into tribes separated by time itself? For now, the Kelly twins remind us that even in our cosmic backyard, time is anything but absolute. And speaking of bending reality, our next stop is even stranger. A hypothetical shortcut through space-time where time doesn't just slow down, it twists into loops. Welcome to the wild world of wormholes. Now, let's take a detour into one of the most mind-bending concepts in physics: wormholes. These cosmic shortcuts aren't just for hopping between galaxies. They might also let you jump through time. Imagine a tunnel carved through the fabric of space-time, linking not just two distant places but two different moments. One mouth of the wormhole could sit near Earth today, while the other hovers near a black hole 1,000 years in the past. Step through, and you've just become a time traveler. The math behind this is rooted in Einstein's equations of general relativity. In the 1930s, physicists Albert Einstein and Nathan Rosen theorized that black holes might connect to white holes, regions where matter and light spew outward via bridges called Einstein-Rosen bridges. These were the earliest blueprints for wormholes, but here's the catch: natural wormholes, if they exist, would likely collapse instantly under their own gravity. To make them traversable, you'd need something exotic like negative energy or exotic matter to prop them open. Theoretically, this material could defy gravity, pushing the wormhole's walls apart like cosmic scaffolding. But the real headache comes with the paradoxes. Say you enter a wormhole that sends you back to the year 1800. You accidentally prevent your great-great-grandparents from meeting. Poof, you erase your own existence. This is the infamous grandfather paradox, and it's not just a plot hole for sci-fi writers. Physicists like Stephen Hawking argued that nature might have a chronology protection conjecture, a cosmic rule that prevents time travel to the past to keep causality from breaking down. Think of it as the universe's way of saying, nice try, but no. Yet, some theories dance around these paradoxes. The self-consistent universe idea suggests that any time travel action you take was always part of history. If you go back and cause an event, it's because you already did. It's like a snake eating its own tail, a loop with no beginning or end. Quantum mechanics even hints at wiggle room. At microscopic scales, particles can seem to influence events in their own, pass through phenomena like retrocausality, blurring the line between cause and effect. So, could wormholes ever be more than math on a page? The answer hinges on mysteries we're still unraveling: dark energy, quantum gravity, and the true nature of spacetime. For now, they remain a thrilling what if. But if they're possible, the implications are staggering. Wormholes could stitch the universe together like a quilt, linking epochs and civilizations across cosmic time. And that brings us to our next puzzle. What if the universe itself is infinite, hosting endless versions of you in an endless sea of time? Now, let's stretch our minds even further with a paradox that turns infinity into a playground, the infinite hotel. Imagine a hotel with an endless number of rooms all occupied. Yet, when a new guest arrives, the manager simply shifts each guest one room over. Room 1 moves to room 2, room 2 to room 3, and so on. Suddenly, room 1 is vacant. Welcome to Hilbert's Hotel, a thought experiment dreamed up by mathematician David Hilbert to reveal the bizarre logic of infinity. Here's where it gets wild. If the universe is infinite, it doesn't just mean space goes on forever. It means every possible configuration of atoms, every version of you, every alternate history must repeat endlessly. Picture this: somewhere out there, a copy of you is reading these words in a universe where dinosaurs never went extinct. Another version is a pirate sailing the cosmic seas. In an infinite cosmos, every life you could have lived isn't just possible, it's inevitable. This ties directly into quantum multiverse theories. Take the many worlds interpretation, which suggests every quantum decision spawns a new universe. Did you turn left today instead of right? Both choices happened, splitting reality into branches. Now layer that onto an infinite universe. Suddenly, those branches aren't just diverging, they're recycling, with infinite variations of you exploring every conceivable path. But infinity isn't just about repetition, it's about scale. In Hilbert's Hotel, you could fit an infinite number of infinite guest groups by shuffling rooms in clever ways. Similarly, an infinite universe could contain infinite Big Bangs, each birthing its own cosmos within a grand multiverse. Some physicists even speculate that our observable universe might be a tiny bubble in this froth of infinite creation. Of course, infinity breaks our intuition. How can copies of you exist if space is expanding? Wouldn't light from those alternate yous never reach us? These are the puzzles that keep cosmologists up at night. But the infinite hotel reminds us that the universe doesn't owe us logic we can easily grasp. It's a place where time and space twist into shapes we're only beginning to imagine, and that leads us to our next revelation. What if time itself flowed differently in the early universe? Here's the next section of the script, seamlessly continuing from the previous segment while introducing fact 25. Now, let's rewind the cosmic clock to a time when the universe was just an infant, a seething, dense fireball where the rules of time itself might have been different. Picture this: in the first moments after the Big Bang, the universe was so unimaginably hot and dense that even time could have been distorted. Some physicists propose that time didn't just flow uniformly back then, it might have moved slower, like a river clogged with debris. Here's why. Our modern sense of time relies on atomic vibrations, the steady ticking of cesium atoms in atomic clocks. But in the early universe, energy levels were so extreme that atoms couldn't even form yet. Space was a churning soup of particles crashing together at near light speeds. Under those conditions, the very ticks of time might have stretched, making seconds feel longer than they do today. Think of it like a high-speed camera trying to film a firework explosion. Everything appears slower in the thick of chaos. This idea isn't just speculation. Theories like loop quantum gravity suggest that the fabric of spacetime could have been granular in those early moments, like a pixelated image. If time itself is made of tiny, discrete chunks, Planck time, the shortest possible interval, then the extreme density of the early universe might have stretched those chunks, altering how time flowed. It's as if the universe's heartbeat was slower when it was younger, pounding once for what we'd now count as multiple beats. But how would we even test this? Surprisingly, there's a clue in the cosmic microwave background, the afterglow of the Big Bang. If time moved differently back then, subtle imprints in this ancient light could reveal it. Some models even predict that certain quantum fluctuations frozen into the early universe might carry a signature of this slowed time. It's like finding a fossilized ripple in space-time itself. Of course, this bends our everyday intuition. We're used to time as a constant, unchanging backdrop, but the early universe reminds us it's more like a stretchy fabric, warped by energy and gravity. And if time could slow down once, could it speed up elsewhere? That's a mystery for another moment. For now, let's turn to an even stranger question. What if some particles already exist outside time altogether? Here's a mind-bending detour into one of cosmology's strangest thought experiments, something that might make you question whether you are even real. Imagine floating alone in the vast emptiness of space with no stars, no planets, just an endless void stretching infinitely in every direction. Now picture this: due to pure, random quantum fluctuations, a fully formed brain complete with memories, thoughts, and even a sense of identity suddenly pops into existence, convinced it's a living person in a real universe. That's the essence of the Boltzmann brain. This bizarre idea comes from Ludwig Boltzmann, a physicist who grappled with entropy and the nature of time in the late 19th century. His theory suggests that, given enough time, like infinite time, even the most wildly improbable events must happen. Think of it like rolling a dice forever. Eventually, you'll land on a million sixes in a row. Similarly, in an endless universe, random particles could, by sheer chance, assemble into a self-aware consciousness, complete with false memories of a past. Here's where things get unsettling. If the universe truly lasts forever, Boltzmann brains should statistically outnumber real, organically evolved minds like ours. So, by pure probability, you might be more likely to be a momentary flicker of awareness in the void than an actual human living on Earth. It's a cosmic existential crisis wrapped in physics. But don't panic just yet. Most physicists argue that if Boltzmann brains were possible, we'd see evidence like phantom memories or glitches in reality. Instead, the universe appears stable and ordered, suggesting we're probably not accidental consciousnesses. Some theories, like the idea of a finite universe or cosmic inflation, also limit the conditions needed for these freak occurrences. Still, this thought experiment forces us to ask profound questions. What is consciousness? How do we know our reality isn't just a fleeting statistical fluke? And if time truly is infinite, does anything we experience actually matter in the grand scheme? The Boltzmann brain might just be a hypothetical nightmare, or the ultimate reminder that reality is stranger than fiction. Now, let's shift to something equally bizarre but far more tangible: particles that seem to defy time itself through quantum entanglement. Now, let's dive into one of the most baffling phenomena in physics: quantum entanglement, where particles seem to break the rules of time and space. Picture two particles, like electrons or photons, that become entangled. No matter how far apart they are, whether across a room or on opposite sides of the galaxy, they remain mysteriously linked. Change the state of one and the other instantly responds, as if they're sharing a hidden conversation faster than the speed of light. This eerie connection disturbed even Albert Einstein, who famously called it spooky action at a distance. He argued that if information could travel between particles faster than light, it would violate his theory of relativity, which states that nothing can outpace light speed. But experiments have proven entanglement is real. In labs worldwide, scientists have separated entangled particles by vast distances and observed their synchronized behavior, defying classical physics. So, how does this defy time? Imagine one particle's state is measured here on Earth, while its entangled partner is light years away. The distant particle seems to know the measurement outcome instantly, no delay, no signal, just instantaneous correlation. It's as if time doesn't apply to their connection. Some theories suggest this hints at retrocausality, where future events influence the past, or time-symmetric physics, where cause and effect can flow both ways. Here's where it gets even stranger. Quantum entanglement might imply that time isn't the linear, one-way street we experience. At the quantum level, particles could be operating outside our usual understanding of past, present, and future. This challenges everything we thought we knew about causality and raises wild possibilities like effects preceding causes, or the universe acting as a seamless whole where time is just an illusion. Of course, this doesn't mean we can send messages faster than light or build time machines yet. The rules of quantum mechanics prevent us from exploiting entanglement for communication. But it does open doors to radical ideas about how time truly works. Could entanglement be a clue that time is more flexible, more interconnected than we ever imagined? One thing's certain, the quantum realm continues to defy our intuition, leaving us with more questions than answers. Next, we'll confront a chilling statistical argument about humanity's timeline, one that suggests our future might be shorter than we think. Now, let's shift gears to a thought experiment that forces us to confront a startling possibility. What if humanity's time is running out faster than we realize? This is the doomsday argument, a statistical twist that uses simple probability to estimate our species' future. Here's how it works. Imagine you're a random human born at any point in history. Statistically, you're far more likely to be born during a period when the population is large rather than small. For example, roughly 1 in every 10 humans who have ever lived is alive right now. That means if humanity survives for millions more years with trillions of future people, the odds of you being born in this tiny sliver of time, the early 21st century, would be astronomically low. The argument suggests a grim conclusion. There probably won't be trillions of future humans. Instead, the math implies our total population might cap out in the billions, meaning humanity's timeline could be much shorter than we'd hope. Think of it like drawing a random number from a jar. If you pull out the number 95, it's more likely the jar holds 100 numbers total, not 1,000. Similarly, finding yourself alive today hints that humanity's jar of total people might not be as deep as we assume. But let's debate this. Critics argue the doomsday argument relies on flawed assumptions like treating human births as random lottery picks when they're influenced by countless variables from medicine to culture. Others point out that it doesn't account for humanity's potential to colonize other planets or achieve near immortality through technology, which could stretch our timeline far beyond Earth's limits. And then there's the psychological angle. This argument feels like a self-fulfilling prophecy. If we accept doom as inevitable, might we stop trying to avert it? Yet the doomsday argument isn't purely pessimistic. It's a wake-up call. If there's even a small chance it's correct, it underscores the urgency of tackling existential threats, climate change, nuclear war, rogue AI, that could cut our story short. It's also a humbling reminder that time for our species isn't infinite. Statistically, we might be closer to humanity's final act than its opening scenes. So, is this a statistical fluke or a legitimate warning? The debate rages on. But one thing's clear, whether you buy the argument or not, it forces us to confront how fragile our place in time might be. Up next, we'll explore an even more mind-bending idea. What if time behaves completely differently in other dimensions? Now, let's stretch our imaginations beyond the familiar bounds of space and time, because what if time isn't just a line we move along, but a dimension we could walk through? This brings us to the wild idea of time in higher dimensions. According to string theory, our universe might have more than the 4 dimensions we experience, 3 of space and 1 of time. Some versions of the theory suggest there could be 10 or even more dimensions, curled up in ways too tiny for us to perceive. But here's where it gets really strange. In these higher dimensions, time might not behave the way we're used to. For beings living there, time could feel like just another direction to move in, like left or forward. Think of it like the classic thought experiment from Flatland, where 2-dimensional creatures can't comprehend the 3rd dimension. To them, a sphere passing through their plane would appear as a circle that grows and shrinks mysteriously. Now imagine we're the Flatlanders and higher dimensional beings can see time as a spatial axis. They might walk through past and future the way we walk through a room, witnessing events as fixed points rather than a flowing sequence. Your birth, your first steps, your last breath all could be laid out like landmarks on a map, eternally present. This raises mind-bending questions. Could these beings interact with different moments in time as easily as we rearrange objects on a table? Would causality, the idea that causes precede effects, even make sense to them? In their reality, the arrow of time might be meaningless, with events unfolding in ways that seem chaotic or reversed to us. Some physicists even speculate that phenomena like quantum entanglement, where particles instantly influence each other across vast distances, might hint at hidden dimensions where time operates differently. But let's ground this in science. While we can't observe higher dimensions directly, their mathematical fingerprints appear in particle physics experiments. For example, the way gravity weakens so dramatically compared to other forces could be explained if it leaks into extra dimensions. And if time is fundamentally tied to these dimensions, it might help explain why our universe's laws seem so finely tuned for life, because other versions of time could exist in parallel, each with its own physics. Of course, this is all speculative. We're like ants trying to comprehend a skyscraper, but the beauty of these ideas is how they push us to question the very nature of reality. If time can be a spatial dimension somewhere else, what does that say about free will, about memory, about the meaning of now? It's a reminder that the universe is far stranger than our everyday experience suggests. And with that, we're ready to confront the ultimate mystery: what happens to time when the laws of physics themselves break down? But now, let's venture into the deepest unknown, where time itself ceases to exist. We've arrived at the eerie realm of black hole singularities, places where the fabric of reality unravels completely. At the heart of every black hole lies a singularity, a point of infinite density where gravity becomes so intense that space and time as we know them simply stop. Picture this: if you could somehow survive falling into a black hole, time would slow to a crawl as you approach the singularity, stretching seconds into eternities. And then nothing, no past, no future, just a state beyond time, a no-hun where the laws of physics as we understand them dissolve into chaos. This isn't just science fiction. The equations of general relativity predict singularities, but they also reveal their paradox. At these points, matter is crushed into zero volume, and space-time curvature becomes infinite. Even Einstein himself struggled with what this meant. It's as if the universe has built-in off switches for reality, places where our theories hit a wall and whisper, "Here be dragons." Enter Sir Roger Penrose, the Nobel Prize-winning physicist who proposed a radical solution: conformal cyclic cosmology. Imagine our universe's distant future, trillions of years from now, when black holes have devoured everything and even light has faded. In this cold, dark epoch, Penrose suggests that the universe's expansion stretches space-time so thin that it effectively resets, erasing distinctions of scale and time. The remnants of our universe could then become the seeds of a new Big Bang, birthing a fresh cosmos from the timeless wreckage of the old one. In this mind-bending model, singularities aren't just in points. They're bridges between universes where time is irrelevant and existence cycles endlessly. But here's the kicker: if Penrose is right, the cosmic microwave background, the afterglow of the Big Bang, might contain faint imprints of past universes. Some researchers claim to have spotted these Hawking points, circular patterns in the sky that could be echoes of ancient black holes from a universe long gone. If confirmed, it would mean our universe is just one page in an infinite cosmic storybook, with singularities serving as the binding between chapters. Yet for all its elegance, this idea leaves us with haunting questions. If time vanishes in singularities, does causality, the chain of cause and effect, vanish too? Could information swallowed by black holes re-emerge in a new universe, like a message in a bottle tossed into an ocean of time? And if universes recycle, does that mean every possible version of you will live again in some form forever? The truth is, we're peering into the abyss with nothing but math and imagination. Singularities remind us that time, for all its power over our lives, might be a fleeting illusion in the grand scheme. And with that, we've reached the edge of human understanding, where the known universe ends and the true mysteries begin. What lies beyond? That's a story even time hasn't written yet. And now, as we bring our journey through the mysteries of time to a close, let's take a moment to reflect on just how bizarre and beautiful the universe truly is. From the way time slows near black holes to the mind-bending idea that it might be an illusion altogether, we've explored corners of reality where the rules we take for granted simply don't apply. Think about it. Time isn't some steady, universal clock ticking away. It's fluid, stretching and warping under gravity's grip, freezing at light speed, and maybe even disappearing entirely inside a singularity. And yet, here we are, tiny specks on a pale blue dot, trying to make sense of it all. Consider the paradoxes we've uncovered. Time travel to the future isn't just sci-fi, it's physics, proven by atomic clocks on airplanes and astronauts aging microseconds slower in space. The universe's expansion means light from distant galaxies will one day fade from view, leaving future civilizations with a night sky emptier than ours. And if time is quantized, as some theories suggest, then reality itself might be pixelated, unfolding in tiny, discrete jumps too small for us to perceive. Even entropy, the relentless march toward disorder, gives time its arrow, yet in time crystals, matter defies this law, oscillating in perpetual motion without energy. But here's the most humbling thought of all. We're peering into these mysteries with tools and minds shaped by the very time we're trying to understand. Our perception of past, present, and future might be nothing more than a quirk of consciousness, a way for our brains to make sense of a universe where, at the deepest level, all moments could exist at once. Whether time is fundamental or emergent, whether it had a beginning or cycles endlessly, one thing's certain: the more we learn, the stranger it gets. So where does that leave you? Right here, right now, in a fleeting sliver of the cosmic timeline. Whether you're team block universe or team time is an illusion, whether you're dazzled by wormholes or haunted by Boltzmann brains, remember, you're part of this story. A story written in the fabric of space-time itself. Now, we'd love to hear from you. What's the most mind-blowing fact about time that stuck with you? Was it the twin paradox, the idea of a universe recycling itself? Or maybe the eerie silence of the Fermi paradox, hinting at civilizations lost in time? Drop your thoughts in the comments below. Let's keep the conversation going. And if you enjoyed this journey through the weirdness of time, don't forget to like, subscribe, and hit that notification bell so you never miss another dive into the universe's greatest mysteries. Thanks for watching, and remember, in a cosmos where time bends, warps, and maybe even loops, the only constant is curiosity. Keep exploring.